In this video, I'd like to talk about momentum contrast or MoCo for unsupervised visual representation learning from Facebook AI research, which is published in CVPR 2020. The reason why I'd like to talk about this paper is because it gives us a new insight of how can we use the concept of contrastive learning more efficiently for the task of computer vision. So let's just talk about that. When we look at unsupervised learning in NLP, this is what we have. We have a neural network, for example, BERT model, and during pre-training, we give it a sequence of words as the input. For example, I love mask token vision. And giving them as the input, our neural network is responsible for predicting what is this missing mask token, and then outputs this missing mask token, and our sequence would be like I love computer vision. So one way of looking at this problem is that we have a dictionary of all the possible words that we can replace with mask token, and our neural network is responsible for finding the correct key, in this case computer, and apply some loss function between the query, our mask token, and the corresponding key in this dictionary. An analogy of this in computer vision would be something like this. We have an input image and we give it to an encoder which outputs some high-level features of it. And then our dictionary would be features of all the possible images that we might have, and our job is to find the correct feature from this dictionary and apply some loss function between query and key. And now you might wonder why we have only an encoder. Why not having an encoder just to encode it and then some decoder to reconstruct it and have some output image? And then our dictionary would be some keys of images instead of features of images, and we simply should compare the reconstructed image with the corresponding image in this dictionary. Well, that would be mask autoencoder, which I also have another video for it from this video, which you can watch if interested. But here we are having a different perspective. We are having only the features extracted from this image, and we apply another concept to deal with this problem, and that is contrastive learning. In contrastive learning, we have a batch of images, as you can see from the bottom right, and we only extract one of them, for example, horse image. And giving this horse image to the encoder, it extracts some features out of it. But for this batch of images, we can apply some data augmentation such as color jittering, applying some mirroring and that type of things, and then pass them to the encoder so that we construct our dictionary, some features of the augmented version of this image. And since we already know which one of them is coming from this augmented version of this horse image, we can simply pick that from our dictionary and apply some loss function between that feature and the feature coming from the encoder from the left side, which is the original image. And now you might wonder, what is this loss function and what is the role of it? Well, in contrastive learning, we have a solution space that our query and all our keys are located inside that. And our job is apply some loss function to pull the query and the positive key from this dictionary to a single area of the solution space to be very close to each other. And for all the negative keys which are coming from a different image, we want to push them away in a different area. But why we do this? Because if we push all the negative keys to one side and pull all the positive keys to one side, we can have a better decision boundary to distinguish it and do our classification, for example. But how can we apply this loss function? This is the formula that you can see, which is negative log of this term. And we want to minimize it for sure. So by minimizing this negative log, we want to maximize what it is happening inside this term. Why? Because log is always increasing as we increase the value, and if we want to minimize the negative log, we need to maximize what it is happening inside. And inside we have this term, and for maximizing it, we need to maximize the numerator and minimize the denominator. So how can we do this? Well, in numerator, we have exponential of dot product of the query and positive key. And we know that dot product of query and positive key is norm of each vector times the cosine of the angle between them. So we want to maximize this term. And for maximizing them, we can either increase the vector length of the query or positive key, or we can make this cosine term maximized. And we all know that the cosine is a value between -1 and 1. So for maximizing it, we need to make this 1. And that only happens when the angle between query and positive key is 0, right? So by making the angle 0, we want them to point in a single direction, and in our angular space, they are as close as possible. But what about the denominator? The denominator is for all the negative keys. And we also have a dot product, and for minimizing that, we want to make this cosine to be -1. In other words, make the angle 180 degrees, which makes them point in an opposite direction. In other words, we want to push them away. And what about this tau term? That is temperature, and that's the only purpose of using it is to make this softmax term to be smooth as possible. And yeah, that's the whole concept behind it. And you might wonder, can't we add a data augmentation before this encoder? Actually, yes. And in implementation we do, because if we apply some data augmentation here before this encoder, and that basically means that we are having two different augmentations for a single image, and we want to compare the features extracted out of them to be as similar as possible. And that is actually better because in different epochs we are applying different type of augmentations, which makes our network more robust against data augmentation and learn a better representation from this image. Hope it all makes sense, because now I'd like to talk about when this momentum contrast shows up. Well, the thing is, if I have a larger dictionary here, that means I have more negative samples. So I have to push more negative keys away from this query. But as I increase the dictionary, the likelihood of happening a similar image as our horse image is more, right? We might see a donkey image, and the features extracted from that image is more similar to this horse, which makes the task more challenging for our neural network to push the extracted features of the augmented version of that donkey image away from this horse image. So that's a good thing, as I have more negative keys in our dictionary, but the thing is that the keys from this dictionary are coming from this batch of images. So I have to increase the batch size to have a larger dictionary, but I can do it to some extent, and I have a limitation in GPU memory, so I cannot just increase it to some very large value like thousands of images in a single batch, which makes the task more challenging. And this is where momentum contrast shows up, how to make this dictionary independent of batch size. So one naive solution, it could be, in addition to have this current batch, we can also have the extracted features from the previous batches in our dictionary. But the thing is that we constantly evolve our encoder, right? So the features extracted from the previous batches are coming from the encoder, but with different weights and biases, because we are constantly updating them in our neural network as it evolves during the training. So since those are coming from different encoder with different weights and biases, I mean the previous ones, the features extracted are not actually the same thing. So it's not the correct thing just to compare them and push them away or pull them to a single location. So the challenge now is that these are not consistent. How can we make them consistent? And in momentum contrast, it proposes a very intelligent technique just to make it consistent. So it proposes to use two encoders instead of a single encoder. An encoder for query and another encoder for key. But you might say, okay, we have different encoders, but we again need to update both of them at the same time. And the problem persists because the encoder key for the current batch has a different weights and biases compared to previous batches. So it is still not consistent. But in momentum contrast says, okay, now that you have two different encoders, you can update the weights of encoder Q with gradient descent the usual way, but for the key, you have to use this formula, which is exponential moving average, which says the updated parameters of the encoder key is m times the current parameters of the key plus 1 minus m of the parameters of query. And in practice, this m should be a value very close to 1, like 0.99. So it says we need to multiply the current parameters by 0.99 and multiply the updated parameters of query by 0.01 and then sum together to make the updated parameters of encoder key. This could be a bit baffling, but the intuition behind this is that I want to keep the current weights of our encoder key as much as possible by multiplying by 0.99, but at the same time I want to improve it. So I add the parameters of encoder Q, but by multiplying it by 0.01. So it slowly evolves the encoder key, but now if we look at the current batch and the previous batch, it is not that different because the parameters are changed slowly, and the representation from current batch, even though it is a bit different from the previous batch, it is not making it inconsistent. But still we have an issue because we are constantly evolving both our encoder key and encoder query. And encoder key, okay, it evolves slowly, but what about after a couple epochs? Then the current batch and the one that it is coming from 100 batches ago, that is completely different, right? Because we are applying some small steps for evolving the parameters of encoder key, but after 100 steps, those are actually big. So we need to have a queue for storing this batch of images, and the size of Q is a hyperparameter, for example, I don't know, 50 or something. And when it reaches the number of 50 and we have a new batch, we add this new batch to the queue and we get rid of the oldest one and dequeue it from our defined queue. Hopefully it makes sense, but that's the whole idea behind momentum contrast, just to make this dictionary size independent of our batch size and store a larger dictionary. And now let's just see the pseudocode of MoCo in a PyTorch-like style just to make it more comprehensible. So we have a FQ and an FKey, which are our encoders for the query and key. And we also have a queue, and it is defined as a dictionary as a queue of k keys. So each key is a c-dimensional vector. So our encoder key should receive an image as the input and output a c-dimensional vector representing that image. And we have k vectors out of them. So the dimension of this queue should be c times k. But remember, this queue, all of them are coming from previous batches. I mean, in implementation, it is a bit different than what I said in theory. It's in the queue, it only stores the ones from previous batches, and it considers all of them as our negative samples because those are different images. And you might say, what if in our previous batches we have the same image but in a different viewpoint, like a same class but in a different image? Well, that could happen, but unfortunately we consider also that as our negative samples because we are about to do this in an unsupervised way, and in unsupervised learning we don't really know what is the label, which is one of the downsides of applying this technique. But anyway, that is what it is. And just to say, before looking at the code, I just want to say that this queue only has the k keys, and all these k keys should be considered as our negative samples. Okay, now let's just look at the code. We have a loop statement for x in loader, and in this loop statement, we load a mini batch of n samples. So our batch size should be n, and we have n images that we augment them, but 2 times. In one time, we augment them so as to have the input for the input encoder queue, but one additional time we do this for encoder key. And then we forward them to the query encoder and the key encoder and have our representations stored in queue and key. But we apply key.detach because we do not want to update the encoder key with gradient descent. Okay, then we apply batch matrix multiplication between query and key. So batch matrix multiplication basically says we have n samples of query and n samples of key. We can simply apply the dot product one by one, and since the first input of the query is the same image as the first input of the key but in different data augmentations, if we multiply them together, those should be considered as our positive samples. And similarly, the second of the query is coming from the same image as the second element of the key, and if we multiply them again, I mean the dot product, that should be again considered as our positive samples. So we have n samples, and we know that the output of the dot product is only a single element. So we have n times 1 dimensional tensor in our positive logits. But what about the negative ones? As I said, we considered all of the ones that we have in our queue as our negative samples. So when we multiply that with the query, we consider all of them as our negative logits. And each of these n samples that we have in our mini batch is compared with all the key elements that we have in the dictionary. So the result is n times k. And then one thing happens which doesn't fully make sense to me. They concatenate these two things together, and then they initialize the labels as some n-dimensional vector, which all of them is 0, and then they apply this cross-entropy loss, which should be equivalent as this equation that we have for contrastive learning. But to me, it doesn't make sense because our labels are all zeros. And in cross-entropy loss, we multiply the label by log of the predicted logits, right? And if the label is all 0, then the coefficients that we multiply with the log should be all 0. So how can we have this formula? I guess to me, the first element of these labels after making this 0 n-dimensional vector, we need to make the first entry as 1. Why? Because the first entry are positives. And then when we apply this cross-entropy loss, for all the negative samples, we have a coefficient of 0. We do not have those logs in our loss function. But for the first element, which is the positive, we have this cross entropy, which is -1 times the log of this term, which is exactly like what we have. But for some reason, they do not include this label 0 to be 1. Doesn't make sense to me. If you do, please just comment in this video. I would be much appreciated. But that's what they provided in the paper. But anyway, they do this loss.backward, which updates only the query encoder. But for the key encoder, they say we have this exponential moving average, which is m times the current parameters plus 1 minus m times the parameters of the updated encoder query. And then the NQ, this new extracted features of the current mini batch, and DQ, the oldest one. So the next loop, again, the Q is having all the negative samples, but instead of having only a single batch, it has multiple batches, which is a hyperparameter that how long we want our Q to be. So yeah, that's all the thing behind it. And there are actually a couple additional notes. For example, how to make prediction with this approach, because it only tries to push all the negative samples away and pull the positive sample in an area of our solution space. Then what? Well, then we freeze the weights of our neural network, which I mean the encoder query, and then we need to add a classifier, just some fully connected at the end of that encoder query and train that. So we throw away the encoder key and we freeze the weights of the encoder query, and by adding a classifier, a fully connected at the end, we can train that. Just train that fully connected layer for the task of whatever thing that we have. It could be an image classification or detection and that type of things. But one additional thing is that batch normalization prevents the model for learning good representations, which the authors figured that out during their experiments. At first, it is a bit surprising, but then it makes sense, because when we have batch normalization in our model, then, for example, let's just say I have 4 images, all right? So for these 4 images, when I apply this batch normalization, it passes some batch statistics from one image to another. And this batch normalization also has some learnable parameters, gamma and beta. And our neural network has to optimize itself to minimize a loss function. So it might learn in a way to learn some gamma and beta so as to differentiate those learned representation of each image, just to make our loss function minimum. But that's not the only thing we need, because in addition we also need to learn a good representation from this image, not only distinguishing them. So just to solve this issue, they are proposing shuffling batch normalization. And in shuffling batch normalization, they say when we are having like 4 images, we can use multiple GPUs. So for the query, the image 1 and 2 goes to a GPU and it predicts something. And for the image 3 and 4, it goes to another GPU and it predicts something. And the batch statistics from the GPU 1 and GPU 2 is different for sure. So when we look at the output, the first image and the second image are sharing some batch statistics, and third image and fourth image are sharing different batch statistics. But just to make this different for our encoder key, we can apply some shuffling and then pass them to 2 different GPUs. And when we look at this now, instead of image 1 and 2 to share some statistics, now image 1 and 3 are sharing some statistics. And likewise, instead of 3 and 4, now 2 and 4 are sharing some statistics. And since for the query and key, these are now different, it should kind of mitigate the issue that we have. And for sure, after that, we can unshuffle it back to the original ordering just to apply our loss function the way it is. And while looking at the result, we can see that these are all unsupervised learning for the task of image classification on ImageNet, which is interesting because by applying momentum contrast in an unsupervised way for ImageNet that has 1000 labels of this image, we can get an accuracy of 68.6 when we are having ResNet 50 wide 4 as our backbone. But for the case of using a regular ResNet 50, it is 60.6. And there was another paper actually within that year called SimCLR, which I will talk about it later, that how can we use that technique just to improve this 16.6 to a larger number, and that is MoCo version 2, which I'm about to talk about them in a minute. Another thing is that we can use the same idea for object detection. Here is the output, the average precision for the Pascal walk test set. We can see that the average precision 50 for supervised version counterpart is 81.4. And if we do the same thing for MoCo, it is actually a bit worse than that. But the thing that it is good now is that we are doing unsupervised learning. We do not need any labels anymore for the test, for the pre-training stage that we want to only do the pulling and pushing. So we can do this with Instagram 1 billion image and then do that, adding the classifier at the end and the object detection. And if we do that, we actually get 0.2% better compared to the supervised counterpart. And if we change the backbone, we can see that in both cases, even with pre-training with ImageNet, we can again achieve a better performance compared to supervised counterpart. And this is for Pascal walk again, but instead of test set, it is train eval. I'm not saying much about this, but we can compare it with other unsupervised learning counterpart and see how better MoCo is. Okay, so enough of MoCo. As I said, we are having MoCo version 2, which is using additional techniques that it is proposed in SimCLR paper, another paper in 2020 that uses contrastive learning and interestingly achieves a better performance than MoCo. But the authors of MoCo realized that we can use the same techniques here again and achieve a better performance again compared to SimCLR, that is MoCo version 2. But in a nutshell, what we are having in SimCLR is that we can use MLP head instead of fully connected layer, as I said. So I said we freeze the weights and add a fully connected for the classification. But now instead of fully connected, we can have an MLP, and that makes sense because MLP is having multiple layers and it can have a more flexible decision boundary just to do the classification. And another thing is that we can have stronger data augmentations, which I won't talk about the details, but if you're interested, you can just read that SimCLR paper for what type of data augmentations that we can do to have a better performance. But the thing is that we can use those same ideas for MoCo, and that is MoCo version 2. And in this table, we can see that the second row, as I said, 60.6 is the one we can achieve when we are using ResNet 50 as our backbone. As I change that from fully connected to MLP, the accuracy increases from 60.6 to 66.2. That is too interesting. If I add only data augmentations, it again becomes better. If I do both of them at the same time, it becomes 67.3. And also we can add a cosine learning rate schedule as it is proposed in SimCLR to make it even better. And finally, by increasing the epochs from 200 to 800, we can make it 71.1. So from 60.6 to 71.1 for ImageNet accuracy. But for Pascal walk detection, it is just make it a bit better from 81.5 to 82.5. And by the way, For MoCo version 1, they also did a couple experiments on MS-CoCo dataset, but I'm not providing this in this tutorial. If you're interested, you can just take a look at it. And this is the comparison between MoCo SimCLR and MoCo version 2. So SimCLR was a bit better than the MoCo version 1, but MoCo version 2 proves that we can use the same techniques that SimCLR provided with the proposed method in MoCo version 1 and even improve it further. But another interesting thing is this table at the bottom that shows since SimCLR is an end-to-end, if we want to have larger batch sizes, we need to have more GPU memory just to make the performance better. But for MoCo, that is not an issue because we can only have a small batch size but increase our dictionary size, and that's the advantage of using MoCo over SimCLR. So okay, that was the all thing I needed to talk about this MoCo. If you enjoyed it, don't forget to like and subscribe, and until the next video, goodbye.